Hi, I'm Kevin Dorma. Welcome back to my whiteboard. Today we're going to look at something a little different. We're going to look at a practical application of computational fluid dynamics. Now when we think about computational fluid dynamics, or CFD, we typically think about really complex 3D applications, such as the flow past a wing, or the flow through turbo machinery, or maybe the flow inside a Formula One racing engine. But we can also use 1D solutions, one-dimensional. Now usually we use 1D solutions as test cases for 2D and 3D problems. And two of the 1D problems that I've looked at are the advection or movement of different shapes to test the accuracy of a flux limiting scheme, or perhaps a simple nonlinear problem like Berger's equation to test a brand new finite volume scheme. But there are some practical applications for 1D transient CFD modeling, and this would be applied to processing facilities or refineries. The one that we're going to consider today is modeling the regeneration phase for a molecular sieve, dehydration system for a liquid hydrocarbon, shown here. The case that we're interested in is understanding the cause of a large surge in liquid flow that comes back to the combined feed that goes into the dehy tower right here. So when the regeneration phase begins, there's a large surge of liquid. Now I implemented this CFD model in a Jupyter notebook on my older MacBook Air, and it was written in Python. But for a 1D problem, even something like a Chromebook is fast enough for practical 1D simulations. I'll explain the process for the dehydration of a liquid hydrocarbon. The process begins with a constant flow rate of C3, propane, from some part of the upstream process. It might be a treating system. The liquid hydrocarbon goes through an online treating bed and comes out dry. The water accumulates in the treating bed. We take a slipstream of liquid hydrocarbon, increase the pressure a little bit with a pump, and we run it through a furnace to heat it up and vaporize it. That hot vapor then flows back down through the spent bed, and as it does that, it warms up the bed, displaces all the liquid, evaporates all of the water, or desorbs the water from the molecular sieve, and all this vapor goes into a cooler. Everything is condensed. Water goes out the bottom, and we can dispose of that, and the recycled liquid hydrocarbon goes back up and combines with the fresh feed. And just after light off of the furnace, plant data suggests that somehow there's a large surge of liquid flow rate that is coming from that bed. And this happens for several minutes. Here's what we're going to do. If a simple one-dimensional plug flow model can capture this phenomenon, then we can perhaps use this model to test different light-off schemes to see which reduces the flow surge. I will describe a simple, and I think fairly clever, one-dimensional plug flow model with heat transfer and phase change. The model is developed on my blog at kevindorma.ca, so go over there and find all the math. Then I'll apply the model to the furnace to see how the light-off process produces a large flow disturbance, and then we'll take a look at the plug flow through the dehydration bed to demonstrate how it's warmed up and de-inventoried of liquid hydrocarbon during regeneration. Now, our CFD model must determine how density, or specific volume, volumetric flow, and fluid enthalpy evolve over time in our 1D geometry. And note, we've got three variables that we have to figure out. We need three equations. We also need to determine some way to figure out the amount of heat that is transferred to or from the fluid from our source of heat. And for this whole situation, we'll make the simple assumption of constant pressure. So again, the full model is developed in my technical blog at kevindorma.ca. I'll erase the schematic from the board, and we'll start by writing down a few of the equations that we need. First, we need an equation of state. And this is the relationship between specific volume and the enthalpy of the fluid. Now, a really simple equation of state is based on it's linear. And we know 2 points exactly. We know the specific volume of a saturated liquid, we know the specific volume of a saturated vapor, and between the two, we know that the specific volume of a two-phase mixture is a linear function of enthalpy. Well, we can also extend this out and say that's also true for the subcooled liquid, and we can say it's also true for the superheated vapor. And that's a pretty fair equation of state in the subcooled and the superheated region. Not perfect, but very convenient. And we can write the same sort of equation of state to relate temperature to enthalpy. Temperature is constant in the two-phase region, and temperature decreases in the subcooled region and increases in the superheated region. Okay, so that gives us one of the equations. Now we need a couple more. One that we need is the conservation of mass. And this just says that the change in mass, the change in density or per unit time is equal to the change in flux of mass flow rate, or volumetric flow rate and density over the volume of our domain. And that's equal to 0. So now we have an equation for how the density changes. And now for the trick. And you can see how I derive this little trick in my blog. And we're going to write an equation for the evolution of the volumetric flow. This says that the change in volumetric flow across the distance or volume of our domain is equal to the slope of our equation of state, the change in volume per change in enthalpy, multiplied by the heat flux that we've absorbed. And go through the derivation to convince yourself that this is correct. What this is saying is heat and the thermal expansion coefficient changes the volumetric flow rate. It stretches it out. And this stretching out of the volumetric flow rate causes the density to go down. So we're not actually solving for enthalpy, we're actually solving for density. And this is why this trick is very simple. It helps simplify the problem, because now I have a homogeneous linear system, or I have a homogeneous conservation law. And this is very simple to solve. This is a textbook problem. Go to Randy Levesque's textbook, Finite Volume Methods for Hyperbolic Problems. This is in Chapter 9. Okay, so I've got equation of state, conservation of mass in conservative form, and I have an expression for the change in volumetric flow rate over the domain, and this is a simple ordinary differential equation. Now we've got all the information that we need to write a finite volume solution or finite volume algorithm to solve these equations and see how the density changes over our domain. We're not quite done. We have one more equation that we need. We need an expression for the amount of heat that is absorbed by the fluid, or the heat that's absorbed by the fluid on the inside of the tube. And this must be related to the heat that is provided on the outside of the tube. And what's in between is some thickness of steel wall, which has some thermal mass. So we have a transient heat transfer problem. Go check out my blog, and I've got the derivation there. It turns out it is just an ordinary differential equation over time, and it tells us how the wall temperature evolves and how the absorbed heat evolves. And that's it. Now it's time to look at some results. We'll focus on two different types of results. First, we're going to look at the operating line. This is a plot of enthalpy over the volume of our domain. This is how the heat moves through the vessel. Of interest is the bubble point and the dew point enthalpies. The temperature or the energy below the bubble point is subcooled. Energy above the bubble or above the dew point is superheated, and it's two-phase in between. The other result that we're interested in is the mass flow and how this evolves, or the outlet mass flow and how this evolves over time. This is what is delivered to the next unit operation. And just for reference, the process operates at 2000 kPa, the furnace feed is at 40 degrees Celsius, the bubble temperature is 57 Celsius. Eventually, the furnace outlet temperature is going to be 210 C. The Sieve bed holds 8.4 cubic meters of liquid propane, and it's about 1.4 meters in diameter and 6.1 meters high, and it's got a 25 millimeter wall thickness. And it holds 4.5 tons of molecular sieve. Let's take a look at some results. We will start by looking at the enthalpy profile across the volume of the fired heater. And in this situation, we will ramp up the firing rate from nothing to full fire from 10 to 20 seconds. So over 10 seconds, we will have full fire. And I will begin the animation, and I'm going to stop it right away so I can show you something. Right there. Okay. So as we've added heat, the entire furnace has warmed up. And we can see this very large volume of furnace tube has crossed the boiling point, or the bubble point line, all at the same time. And what this does is this will push out this entire volume, about 0.35 cubic meters of liquid propane, and push it out and send it down to the molecular sieve vessel that's being regenerated. And all of this happens very quickly. So I'll just back it up and we'll see how this whole thing plays out again. So this expansion pushes a 0.35 cubic meter volume of liquid propane out of the furnace tubes into the dehy vessel. And the amount of vapor that we've produced increases from time 37 seconds to 50 seconds. And then after 50 seconds, we're just warming up we're superheating the vapor up to 210 degrees. Now let's take a look at how the mass flow rate through the furnace changes. Our plot of the outlet mass flow looks a little bit alarming. The outlet mass flow increases from 5,000 kilos an hour to 7,200 kilos an hour at 37 seconds. And that isn't really visible on this graph. And this is because the liquid in the tubes is warming up and expanding. So that means the furnace is actually pushing out more liquid than is coming in. But then when all of this liquid hydrocarbon reaches the bubble point and expands, due to producing vapor and pushes out the tubes, we get a mass flow that's over 60,000 kilograms an hour that is heading towards our D-high vessel that is being regenerated. Now this only exists, or this high mass flow only occurs for 5 to 10 seconds. And it might be very difficult to pick up on a data historian because of the data capture frequency that we would have on the historian. But if we were outside looking at analog gauges, like a pressure gauge or a differential gauge, then we could probably see this. And then after 60 seconds, after light off, the mass flow rate out is fairly constant. So this is interesting, but it doesn't represent the observation that we see, which is a large mass flow that's occurring for many minutes. Okay, so let's take a look at the molecular sieve vessel and how this disturbance impacts the behavior of the molecular sieve during regeneration. Let's talk about the vessel. Now, I used the outlet conditions from the furnace as the inlet conditions for the vessel. And this is because it just makes for a faster simulation. Now, the vessel is not heated. The heat flux going into the vessel is zero. It's insulated. Instead, we have a very substantial mass of steel on the outside of the vessel, the steel shell, and the mass of the molecular sieve inside. And this has to be warmed up as the liquid is displaced and pushed out of the vessel. Now, modeling the heat transfer for this is a bit nefarious. We've got both steel and molecular sieve that provide thermal mass, and I need to model the whole thing as a piece of one-dimensional pipe. So I need to sort out some kind of equivalent wall thickness of the steel pipe, and I need to estimate some kind of heat transfer coefficient, and that's also tricky. Now we can estimate the heat transfer coefficient for an individual mole sieve particle. Let's say it's a round particle about yay big, but then we have to convert the whole thing into a heat transfer coefficient for our imaginary or modeled 1.5 meter diameter pipe. So have some fun with this. I'll show you the animation and then I'll walk through it. Okay, there's 3 parts to warming up. Bottom part, middle part, and top part. And I'll stop it right here. The enthalpy profile shows the bed warming up in 3 distinct steps. The first step is from the initial condition of 40 Celsius to the bubble point of 57 Celsius. This moves across the bed rather quickly and reaches the outlet at time 570 seconds, or about 6 minutes. Now, all of the volume to the right of that point is liquid hydrocarbon. Now, close behind this is the rapid increase in liquid enthalpy from 360 kilojoules per kilo to 630 kilojoules per kilo. And this is where the bed becomes more filled with vapor. So this line here, this region here, is where the bed is becoming de-inventoried. So this represents pushing this liquid piston of liquid hydrocarbon out of the bed. And over this region, the temperature is remaining constant. Now the slowest step is where the superheated propane is warming up the bed. We no longer have liquid enthalpy or liquid to push out, it is just vapor, but we have to warm up the bed from 57 Celsius up to our final temperature of 210. And that's what this long, very slow-moving ramp or temperature profile of enthalpy is representing. And we can see this pushes across the bed very slowly. And this takes about 3,000 seconds, so almost an hour, for that bed to warm up after all of the liquid has been displaced. Now, this is interesting But on the surface, it doesn't look like we have anything to worry about. But let's go on to the trend of mass flow rate leaving the bed. Well, that's interesting. We have an instantaneous spike of mass flow rate that is pushing 100 tons an hour. It's very short-lived. It's only for a few seconds. And then it drops off to about 30,000 kilograms an hour. Now this is about 60 cubic meters an hour, and this lasts for about 600 seconds, about 10 minutes. And this is the disturbance that we're probably seeing in the plant. Now keep in mind, this represents a large flow disturbance. An additional 60 cubic meters an hour fed or going to our online bed, which took a raw feed of 100 cubic meters an hour, is a really large disturbance. So taking almost double the flow rate, or worse yet, this super high short-term spike of liquid that is approaching 200 cubic meters an hour, that would be an intolerable change in flow rate through that molecular sieve bed. It would introduce a very high pressure drop, could cause equipment damage, it could deform the hold-up plate or the hold-up trays. If it's downflow, it could fluidize the bed. If it's upflow, we may get poor dehydration performance. We could have all sorts of things that happen. Or, if there was a sensitive unit operation on the downstream side, then the flow rate from this light off, or the flow rate upset from light off, would cause a large disturbance to that downstream unit operation, and that means the unit op would run off-spec for some length of time. The great thing about a CFD simulation is that we can try out different light-off sequences to find a method that reduces the flow disturbance to the online molecular sieve bed. And if a simulation looks promising, then we have good reason to convince the plant manager and the operations manager that a plant test should be tried. And the modeling can show us what to look for and where to look for it. And this allows the operations and engineering teams to conduct the plant test so that it produces a conclusive result. And the ultimate objective is to improve the safety and productivity of the facility. Take care.